So this type of shared electron bond is called a covalent bond. And for elements in the second and third row of the periodic table, observational evidence and deduction done in large measure by analyses by G.N. Lewis demonstrates that the requirement for a closed shell requires an octet of valence electrons, where the valence electrons are the outermost electrons constituting the outer shell of the electron distribution around the atom. So for example, if we take a hydrogen atom with a single electron and we form a chemical bond with the chlorine atom has 7 electrons. And when we combine hydrogen with chlorine, we can represent that Lewis diagram as H and Cl, but now we have a shared pair between the hydrogen and the chlorine, and the 1 hydrogen electron contributes to the 7 electrons from chlorine to form that octet. So we have an octet of electrons, and we have a duet of electrons around hydrogen. So in the second and third row of the periodic table, we form these octets, the most stable form, for all of the species except hydrogen, which has the duet. Now the remarkable thing about the Lewis structure, as it's written here, is that this is the lowest energy structure. And it turns out as we get to more and more complex molecules, the Lewis structure tells us more and more about the details of exactly what that structure looks like, and it solves for us on the back of an envelope the lowest energy structure for a given molecule. And that's why it's so important. Now the next thing we want to talk about is a very important aspect of how the periodic table organizes our thinking around the ability of atoms to attract electrons. And this is a very important pattern in the periodic table. And that pattern is that as we move to the right-hand side from the left-hand side, the propensity for those atoms to attract electrons increases. So this increasing ability to attract electrons as we move from left to right in the periodic table is represented by the term electronegativity. And as we'll find, one of the most remarkable aspects of the formation of molecules from atoms is that independent of the molecule, the intrinsic electronegativity of an atom remains largely invariant. And that means once we begin to understand the ability of a given atom to attract electrons to it, we can apply that information, that knowledge, to any molecular structure. And the greater the attractive power of an atom to draw electrons to it, the greater the electronegativity. So when we formed our HCl from combining a hydrogen atom with chlorine, we've taken the formation of the bond between hydrogen atoms that are from the far left side of the periodic table and combined it with chlorine from far right side of the periodic table. So that means that when we analyze this hydrogen atom that reacts with the chlorine atom, it means that while we represent this as a shared electron pair between the hydrogen and the chlorine, in fact, because of the high electronegativity of the chlorine atom relative to hydrogen, that hydrogen electron is actually nearly fully donated to chlorine. Because chlorine is so much more electronegative, it has a much greater ability to attract electrons, so it actually draws that electron in a very significant way away from the hydrogen atom in the formation of that HCl bond. Well, there are important cases, however, where the sharing becomes sufficiently unequal that one of the atoms in the bond effectively removes an electron from the less electronegative species, forming a positive ion, which is called a cation, and a negative ion, which is called an anion. And a perfect case in point is for the metal sodium. This is the metal that we recognized before, that if we drop it into water, it actually explodes, catches fire. And the reason for that is that the electron in sodium is very weakly attached to sodium. And on the other hand, chlorine very strongly attracts electrons. It has extremely high electronegativity. So when we combine this sodium atom with very low electronegativity with chlorine, it turns out that we form a type of bond called an ionic bond. So let's see how this works. We start with our sodium, and there is just one valence electron in sodium. And the inner shell of that sodium structure is tightly bound to the nucleus, and that single electron is forming a new orbit around sodium, and it's very, very weakly bound. And when we react that with our chlorine atom that has 7 electrons and is extremely hungry to add another electron to fill that octet, what actually happens is we now have a sodium atom and a chlorine atom, but the chlorine atom now has 8 electrons around it. But because of its extremely high electronegativity combined with the extremely low electronegativity of sodium, we actually have a case where the sodium has lost its electron and the chlorine has gained its electron. And that's why it's called an ionic bond. The sodium is a cation in that structure and chlorine is an anion. So as we move from left to right in the periodic table, the extreme case is taking one of the metals from the first group of the periodic table and combining that with a halogen at the far right-hand side to create a cation-anion combination that creates the ionic bond.